So we're going to keep on looking into Unit 2, Applications of Mechanics. More specifically, that application of motion. And the motion that we're applying and looking at is that a little bit of stuff that we have covered before. You have seen this before, and that is this idea of parabolic graphs and direct proportion graphs. Nice line. Parabolic has a quadratic aspect to it. Why is this? Because we're going to and why do we bring these ideas back up again? Because now that we are going to be dealing with objects being projected through the air, we need to remind ourselves of the parts that are going to be involved with this. Because solving for some of the times and some of the distances that an object will pass through requires us to be able to solve for things in the x direction and for things in the y direction. Because if we throw something in the air, it's not going to be like, okay, I'm going to move here, and then I'm going to move up. Then I'm going to move X, and then I'm going to move Y. I'm going to move Y, and then I'm going to move X. It does both at the same time. The red line here is what we see. The green and the blue is what's happening to make the red line possible. Okay? If I took and had slopes of lines at specific intervals on the red, I would get roughly the yellow arrows. Those would be like the hypotenuse of a triangle, meaning there is still a x component and a y component to it as it's going through. That fact that it has an x and a y component to it allows us to solve those things, to make it a triangle. Unless you're going to do some calculus, finding the area underneath this curve, triangles are going to be the way to go. Split it up. Okay? It's the same thing as you can use algebra to kind of find the slope of this line. You just have to have very specific parts, and you have to split it up into really small areas. You can use calculus to do that, and it's a little simpler and easier, but that's not where we're at. That's not what we do in this class. So, reminding ourselves of those velocities and those equations from gravity are important. Now, if we recall and look very closely at the equations that we used for when acceleration was constant, a lot of these are going to be the same. The only thing that's missing from this equation is the initial velocity. Because we've dealt with this equation. We did it at very early so far. Usually, the reason why we do that is the initial velocity is usually going to be 0. But now things are being projected through the air. Sometimes that initial velocity might be 0 in the y direction, but have something in the x direction. So because we have to solve for things in two different ways, we have to be reminded that gravity deals with the up and down, the y direction. X is all other motion. The rules that apply to gravity are still there, meaning that when an object is going up into the air, it is going to decelerate at the rate of gravity. As an object is falling towards the ground, it is going to fall at the same rate of gravity. And for our class, we use gravity as 10. Makes the math a little nice. Okay? And for the most part, when we say that gravity is 9.81, it rounds up to 10. We're not going to be that far off. We're going to be close. So those are some of those ideas and concepts still apply, and so that's the important thing. To remind ourselves of an equation that we have used already, what would the speedometer reading on a falling rock be 4.5 seconds after it's dropped from rest? Well, utilizing G times T, we can use 10 meters per second times 4.5 seconds to give us a final velocity of 45 meters per second. Well, what about after 8 seconds? Now, some people would look at it and say, well, it should be slower. No, it's only slower if it's going up. In some cases. It might actually be faster even if it was 8 seconds after it was launched, because if you have an object going up and then coming down, if it's going up at 4.5 but then coming down at 8, you have different things. But that would have to be more elaborated more. You would do the same thing, it's just the time changes to 8 seconds to give us 80 meters per second. 10 times 8. Okay. At this time, again, it's just reminding us of how do I do that? We have to think, and that's why we wait until near the end, or near kind of a little bit later in the year, to talk about projectile motion, because you have to understand motion in one dimension and motion up and down before you kind of combine them. You're like, oh, because they're both happening at the same time. And one does affect the other. So what this does is a ball's velocity has a horizontal and a vertical component to it. Again, we're only going to see the hypotenuse, and the thing that we have to remember is that I can take that and bring it over there to make and complete that triangle. This difficult to solve. closed your triangle, now you're like, oh, I got this now. Being able to move those arrows, and I'm not really moving it up and down, and that's where you don't do it. You just literally shift it to close the triangle is all you do. Whatever's necessary. Some people move it that way. Some people will close the triangle in that manner, where they just take the horizontal and move it up. Does that matter? No, it doesn't at all. Because as we remember, it doesn't matter how we get the triangle, it's always going to be the same. Okay? And so it's like when I talk about sometimes with students, you're like, well, physics is like seeing the matrix. Well, instead of just a bunch of code going down, you see everything in motion and vectors and arrows as things are moving around. As it just you kind of look at some things differently. The more you know, you kind of look at the world differently as it goes through. So, again, constantly reminding ourselves that all vectors have two components. They're going to be at right angles. Why is that important? Because triangles that have a right angle are much easier to solve. We can use sine, cosine, tangent. We can use the Pythagorean theorem in some cases. So those components are very important to us. Some terminology things that we do also have to get taken care of. A projectile's path is called its trajectory. Okay? As we can see in the picture, a object, I think this is great because it has these wonderful things. Slow-mo here. We get to see boom, 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 boom. And the rate in which these are taken are probably the same. But why is it slowing down, and why are the balls or the sphere look like they're getting closer and closer as it's going up to the top? Because it's slowing down, right? And then they get farther and farther apart, almost at the same exact point, right? Why? Well, that's right. Gravity. Doesn't care what it is. It's going to accelerate it or decelerate it, depending on how you want to look at it, at the same rate. Hits the ground. Transfer of energy. Why doesn't it go up there? Transfer of energy. Something we might not get to, or something that's talked about later. Like, even, that would be the perfect golf ball, wouldn't it? Or the perfect bouncy ball. You drop it, and it comes up to the same exact height. That means all of the force that you put into a golf ball, whack. The golf ball then puts back out. And a golf ball, you whack a golf ball pretty hard, it goes pretty far. Hopefully you whack it in a way in which it goes straight, and then it's even better. But it's not, there's some energy lost still. Right? It's a perfect elastic collision is kind of like one of those physics things where they're like, well, it's a perfect sphere. Nothing's really truly a perfect sphere, and there's no air resistance, and there's no friction, and there's no, it's like, well, yeah, it just makes life easy. But it's that parabolic thing that we can see, we literally can see gravity doing this. So another slow motion picture, like this one here, shows us that an object that is projected horizontally does fall at the same rate. The red ball drops horizontally. The yellow ball is shot out. The red ball drops vertically. The yellow ball is shot out horizontally, and yet they still fall at the same rate. So which brings us back to the which hits the ground first is, it might not always make sense that a bullet being dropped and a bullet being shot are going to, if done at the exact same moment, are going to hit the ground at the same time. It's hard to see it, so that's why we have things like this to prove, like, no, this is what it is. But that is part of the whole process of everything falls at the same rate. Gravity doesn't care who you are. You're gonna fall at the same rate. Now it cares if you have a parachute, because that can slow you down, and you're just increasing your surface area, which increases your air resistance, friction. That will allow that to happen. But when we're doing projectile motion, we're not going to deal with that. We're not going to deal with parachutes and things because they complicate things. We're going to try keeping it simple. Okay?